Imagine the universe as a vast, dark ocean. The galaxies we see, those brilliant islands of stars, are like flecks of foam on the surface. But the real power, the immense weight of this ocean, is hidden from our eyes. There is a presence in the cosmos that we cannot see, we cannot touch it, yet we feel its gravitational embrace on everything we can observe. It is the invisible hand that sculpts the shape of galaxies and binds their clusters. This mysterious substance makes up more than 80% of all the matter in the universe. We call it dark matter, unseen, powerful, and profound, our greatest scientific detective story. To understand the search, we must first understand the quarry. What exactly is this dark matter? Think about the solar system, sun, planets, moons, asteroids. All of this is normal or baryonic matter made of atoms, protons, neutrons, electrons. It interacts with light, shines, reflects, absorbs, and casts shadows. But on galactic scales, the numbers did not add up. The math said something was missing. Vera Rubin saw outer stars moving too fast for visible matter to hold. A vast, invisible halo of mass, gravitational glue, must surround each galaxy. Gravitational lensing confirms far more mass than we can see. Even the Big Bang's afterglow carries dark matter's imprint. Leading ideas, new particles outside the standard model. All around us, streaming by, dark because they ignore light, shy with normal matter. Faced with an elusive target, physicists built ever more sensitive detectors. Strategy, brute force, and extreme patience. Make a very large, very clean, very quiet target. Bury it deep to shield from cosmic rays and background radiation. Then wait. Pray. One dark particle bumps a nucleus, like a ghostly cue ball, leaving a tiny flash or heat. Magnificent underground experiments push low background and cryogenic frontiers. Despite years of operation, no unambiguous signal. Maybe WIMPs are lighter, or interact more subtly than collisions. If our net's holes are too big, the fish slip through. So we invent new tools, new lanterns, to probe what our old ones could not. So yeah, our next leap may come from the quantum realm. Superposition, entanglement, waves and particles. Reality gets strange. We now harness these principles for unprecedented measurement. The quantum toolbox, sensors, computers, and networks. Unlike brute force bumps, these tools listen for subtler effects. They can detect infinitesimal shifts in time, magnetic fields, even spacetime's fabric. What if dark matter is an oscillating field pervading space? A quantum sensor is like a perfectly tuned instrument, resonating only with the hum. Using individual atoms or particles as delicate probes, a tiny perturbation becomes visible. Shift the search from rare bangs to persistent modulations. This opens new discovery space and sensitivities beyond classical limits, even surpassing the standard quantum limit with entanglement. And that is where we begin. At the heart of the quantum search are quantum sensors. Atomic clocks lock lasers to ultra-stable atomic oscillations, our most precise timekeepers. The best would not lose a second in 30 billion years, twice the age of the universe. If a dark field makes constants oscillate, a clock's frequency shifts in a telltale wave. Incredibly tiny, yet detectable with state-of-the-art clocks. Magnetometers can sense axion-induced photons or faint oscillating magnetic fields. Ultra-cold atoms and diamond NV centers act as ultra-sensitive quantum compasses. Replace one giant detector with distributed, specialized sensors. Some listen for time shifts, others magnetic whispers, tiny forces, or accelerations. By referencing atomic energy levels, they reach quantum-limited precision. These are our new ears, tuned to the subtle frequencies of the dark universe. Sensors are our ears. Quantum computers are our new theoretical labs. Bits are 0 or 1. Qubits can be both, linked by entanglement. They explore vast possibilities simultaneously. The universe is a quantum system, perfect for quantum simulation. Complex dark sectors overwhelm classical machines. Quantum excels. Program axion mass and coupling, run and predict the exact sensor signal. Experiments tune to the most promising frequencies and recognize true patterns. Results refine models. Models guide searches. A powerful loop. No longer blind, we let simulations light the way. Quantum computers are not just for calculation. They are tools for understanding. A single quantum sensor, no matter how sensitive, can be fooled. Local fields, tiny vibrations, laser fluctuations can mimic signals. We need global correlation. Signals sweeping Earth, not a single lab. Network precision clocks worldwide and look for time-delayed echoes. A dark wave makes them tick together with a predictable delay. Entanglement can boost sensitivity to shared signals, beyond standard quantum limits. Fiber networks and satellite links knit a global quantum observatory. Existing clock networks, and even GPS, are being repurposed to listen. We are learning to see Earth as one vast, synchronized scientific instrument. This is not science fiction. Casper uses nuclear magnetic resonance to seek axion-driven nuclear wobbles. The GNOME network, dozens of atomic magnetometers, hunts correlated transients worldwide. A dark matter wall would sweep sensors with a fleeting magnetic signature. Clock networks at NIST, PTB, and partners place new limits and keep listening. Superconducting qubits can catch single microwave photons from axions or dark photons. Each project opens a new window onto the dark universe. The search for dark matter is deeply human, curiosity refusing to yield. Students, technicians, theorists, many hands, one quest across nations. Along the way, better clocks, navigation, imaging, computing, benefits for all. The universe owes us no secrets, but at last, we can listen in a new way.